All right, welcome everyone. Tonight is our last lecture. We will have a meetup next week at 8 o'clock. It'll probably be shorter, to be kind of mostly introducing the final exam and just some little last minute wrap up stuff, sort of administrative. So there won't be any new topic next week, but we will meet. Um, so we're in the home stretch here. So today we're going to talk about Bayesian and predictive analysis, but I want to actually go back because I think there was a question last week and I've been working. I'm showing something kind of a work in progress in an attempt to kind of clarify maybe a little bit of how multiple regression is going to work. Um, because I was using a app made by a colleague, I ended up, and if you guys are interested, I could certainly share the source code, but um, I am actually using something called Plotly, which I think if you take the visualization course, I think you'll cover Plotly. It's pretty actually simple to work with. So this is the same data set as last week in terms of we're trying to predict depression from affect and anxiety. And I actually have a couple other data sets we could look at here. Um, right. And I showed this in terms of trying to show regression, right? So here I'm calling the LM function. And the question is like these bits, right? These estimates, where is that coming from? Now, I don't really work through how to solve this problem using ordinary least squares because really to do it, um, you need to know some linear algebra, and we don't expect you to know that. We don't actually teach it in the program. Um, and it's a detail. It's nice if you know it, but it's not necessary in order to become an applied data scientist for sure. But when we're doing multiple regression, what we're trying to estimate is the same thing as, right? So this would be a simple linear regression. So instead of a line, we're trying to estimate a plane. And the formulas we use to get this, right, we're still trying to minimize the sum to squared residual. So what I wanted to add, and I couldn't do, but I've been working on this week, is this, right? So when you think about it, when we have two predictor variables, right, we still have our predicted value, which is going to be on the plane to this value. So we're just minimizing that as we go through, and it actually might be easier to show maybe if you give me 1 second. Never mind. From a maximum likelihood estimation, right? I'm going to write this up and I'll post it. It's just not done yet. Right. So we could just set an algorithm where we're trying to predict that. So that's sort of multiple regression in a nutshell. Now, when we add a third predictor variable, there's really no way to visualize this because you have too many. But right, so these lines, right, that's what we're just trying to minimize. Now, when we're talking about interaction effects, right? So, and here's the regression output. So if I say, oh, I'm sorry, I want to add the interaction from the regression output, right? I'm adding this multiple, here. So I actually have a third component. And what that third component does is it allows the plane to kind of warp. And why would we want to do that? So and here what I was showing or trying to explain last week is like when affect is really high, anxiety has less of an impact on depression, where when affect is low, of course this is backwards, right? So this is low anxiety. As anxiety increases, depression is going to increase a lot. So if I could pick here and add simple slope. So if I want to say, we would call this my moderator, and I want affect to be my moderator, right? I could draw these lines. And so this black line here is one standard deviation above the mean on affect, and this is one standard deviation below. So a lot of times when you see interaction plots, if you Google around, this actually, if I get it oriented so low is on the left, right? This is often what you might see is just these two black lines, right? So as anxiety increases, or I'm sorry, as affect increases, the rate of change in depression related to anxiety is going to increase at a steeper slope. So that's what we mean by there being an interaction effect. So if we go to another data set like this poverty data set that we looked at before, where we're predicting poverty from female household and white, right? So this is actually, let me go back, right? If I look at the regular regression, right, this is what we were estimating is this plane. So as these two things kind of vary, we could see how poverty increases. Now, in this case, when I add in the interaction effect, notice how the plane doesn't really warp much, right? And that's because if I go over here and look at the regression output, the interaction term is not statistically significant. So that's to say that there's really no interaction between white and female household, right? I showed this example because this is collinear. In fact, once we have female household, the white isn't even a significant predictor, and that's because these two are kind of related. But what I was main thing I want to take away, right? So we're still trying to minimize the squared residual. So I'm going to take the length of each of these lines and square, and that's what I'm minimizing when I'm doing multiple regression. No matter how many I have, and when I have two quantitative, I can kind of depict it this way, 3 dimensions. I hope this helps give a little bit of clarification on what I was trying to show. And I'm going to write up a document and hopefully have it up in the next couple of days. It's probably like 70% written. Are there questions about that before we move into Bayesian analysis? I'll also post this app that you can play around with. All right, then let's talk about Bayesian analysis. So I'm not going to test Bayesian analysis on the final exam. This is really meant to be actually a lot of what I'm doing tonight is just trying to give a little bit of a jump start to some stuff you're going to do in the rest of the program. But it is also connected to what we've done in this course. The Open Intro book doesn't really, it talks about Bayes' formula, I think, in the probability chapter, just very briefly. Now, if you're interested in Bayesian analysis in greater detail, the book I recommend is Kresge's book, Doing Bayesian Analysis. I also have a link to his YouTube channel. He has a whole bunch of great videos. I think he kind of explains things really well. I'm going to work through an example tonight that I kind of borrowed from Rasmus Bath. To be honest, I'm a trained frequentist. It's kind of like I've been doing this long enough. Bayesian analysis didn't really catch on, particularly in academia, until like maybe the late 80s and 1990s. Oh yeah, I'll post all of the slides too once everything's up. But let me put this link here for the Kresge's YouTube channel. So I'm only over the last few years really starting to see the appeal of Bayesian analysis, and I've used it in a couple of contexts. Now, in the social sciences, not a lot of people publish using Bayesian methods, but I like to talk about it because I think it provides a sort of contrast to the frequentist approach, right? And to summarize, one of the major things I hope you get out of this course is the notion of really the central limit theorem, right? So when we're making inferences, whether it's regression or null hypothesis test or whatever, right, we tend to evaluate it against the null, and we're trying to gather evidence to either reject the null or not reject the null, or figure out if we can, right? We don't prove anything. We're just trying to provide a level of confidence, or what's the probability of the null being true or not, right? And we make that inference based upon the central limit theorem, which says if we could take an infinite number of samples, then that the distribution of our metric, usually the mean, is going to approximate the normal distribution. And so although we don't ever see it, we know it's there theoretically. And so that's how we're making our inferences. Bayesians, on the other hand, are going to say, no, the truth is our data, right? And so what we're going to do is essentially, in most situations, kind of simulate data to see how often we would get with what we got. And it's going to be hopefully a little bit more clear as I work through an example. The last thing I want to recommend is, in terms of like, if you're looking for a kind of an interesting summer read, and particularly if you're into history, is A Theory That Would Not Die. It's not a stats book. It's really more of a history book. And it kind of tracks because Bayes first wrote Bayes' formula, when he wrote his first paper, I think it's like late 1800. So it's been around for a long time, and it's been used in various contexts. Probably the most famous use of Bayes or Bayesian analysis was by Alan Turing. and he used Bayesian methods to and along with the Enigma machine to crack the German codes in World War II. So that was a Bayesian approach that he used. So, anyways, this kind of tracks the history of it and how it's been used in different ways. A lot of times in military uses, but and then how really it wasn't until the prevalence of kind of computers in the 80s that they became more readily available that it took off. And as I go through the example, I think it'll be clear as to why. Um, so and it's from a probability point of view, I could have talked about this when we talked about the probability chapter, right? It's a way of getting conditional probabilities when we know the other parts, right? Or there's kind of, conditions, right? And so this is Bayes' formula in its original form. And, one way we could do it is say if we're trying to understand a positive test on breast cancer. So we have a couple of bits of data, right? Um, this is a little bit dated, so don't take this as sort of any kind of advice, but hopefully you get the picture, right? So based upon survey, we estimate that approximately 1% of women have breast cancer, and so then 99% do not, right? And then 80% of mammograms detect breast cancer when it is there, so therefore 20% miss, and 9.6% of mammograms detect breast cancer when it's not there, right? That's false positive. And then 90.4. And so we could write out this kind of 2 by 2 table. And in a lot of the probability stuff we did, we tried to set things up so the sum of all of the cells is 100, but that's not what we have here, right? We kind of have 1% who fall in this column, and then if you're in this 1%, then there's an 80% chance that test is going to catch it in a 20. And if you don't have cancer, right, the majority of people fall over here, right? 9.6 are going to get that false positive. Okay, so the sum of the columns equals 100, but not the whole table. So then the question is, well, how accurate is the test, right? So if you get a positive result, what's the chances you actually have cancer, right? And so, we could think we could go through and do it this way. It's well, it's a 10% chance, right? Roughly, but it's not quite right. So when we think about probability, we're thinking about the ratio of the desired event against all possibilities. So if we take the Bayesian's formula and we could simplify it, and I'll show it in a second, right? What we want is we know the probability of a positive test given. Well, this is what we want to know is the probability of cancer given a positive test. What do we know? We know the probability of a positive test given cancer. We know the probability of cancer and the probability of a positive test, right? So then if you got a positive test rate, then really it's a 7.8% chance that you have cancer, right? Not 10% as you might intuit. And so Bayes' formula allows us to get conditional probabilities when we know the other conditional probabilities of full one. Now, from a data point of view or from a modeling point of view, kind of going to think about these things a little bit differently, right? So we're going to think about likelihood, right? So in the same way we think about maximum likelihood estimation, where we could look at likelihoods in different ways. And then we have some prior and we have some marginal likelihood, and we want to get a posterior. So, like I said, for me, this example that Rasmuth gave in a workshop probably about 10 years ago is the first time I actually started to get this. And this is actually a problem that I think is pretty difficult to solve using a frequentist approach. And if you read the theory that would not die, a lot of the places where Bayesian analysis was used, and it was in situations where we're trying to do estimations or searching for things or things like that. So let's say we want to estimate the population of a lake or a pond, right? And, we could possibly try to catch them all and count them, but that's not really practical. We can't really do a census on a lake. So we have to come up with some kind of sampling scheme that allows us to get a good estimate. So the strategy I'm going to propose is I'm going to go out in my boat and I'm going to catch some fish. I'm going to mark them and I'm going to return them to the pond. I'm going to wait long enough that they could possibly swim to any place in the pond, right? So that they could shuffle. This is a small pond, imagine, like in Central Park or something. I'm going to go back out and I'm going to catch the fish. I'm going to catch some fish again, and I'm going to count how many are marked. Therefore, we're caught twice. Okay. Let's suppose I do this. I go out, I catch 20 fish, mark them, put them back in the pond, go back out sometime later, catch another 20 fish, and 5 of them are marked, meaning 5 were caught a second time. This is the only information I have, and from this, I want to estimate how many fish are in the pond. So to begin, I need to define some kind of prior. And you could just think of the prior as my initial guess of how many fish are in the pond. So in this case, what I'm going to do is I'm going to use this, sometimes I might call this a naive prior because I don't really know anything about counting fish in a pond. And I think there has to be at least 20 because I caught 20. And it's a small pond. So I just say there can't be any more than 250. I'm gonna have to put a ceiling somewhere because I can't try everything. So I'm just initializing this numeric vector of a length 100,000. And I'm gonna say this, so I'm gonna make 100,000 guesses, anywhere from 20 to 250, and any number in between has an equal likelihood of occurring. So I'm not, so I think 20 fish is as likely as 100, as likely as 150 is as likely as 250. Okay. So this is my prior. And so what I'm going to do is, as we'll see in a moment, is I'm going to loop through this vector and I'm going to say, okay, well, what if there are 233 fish? And I'm going to try to generate some data to see if I would get that 5, right? 94, et cetera, et cetera. So that's my prior. So then the next step is to define a generative function, right? I'm going to generate fake data. And in this case, I need to generate fake data based upon my counting scheme. All right, so I'm going to define a function called pickfish. It takes one parameter. In a moment, what we're going to see, I'm just going to pass these numbers one by one. So I'm going to loop over this function 100,000 times in a minute. So let's say, 233 is my first one, right? So what I'm going to do is initialize a vector where I'm going to have, so I'm going to have zeros and ones. I'm going to have, what did I say it was? 233. Oops. 233. So I'm going to have 213 zeros and 20 ones, right? So I'm going to repeat 0, 233 minus 20, and then 120, right? Essentially, I created a vector to mimic the pond with where I marked 2. Then what I'm going to do is randomly sample from this vector 20 fish. And then I'm going to sum that vector. And since I made it 0 and 1s, that's essentially counting how many fish I caught a second time, right? So then I'm going to initialize another vector. So I'm going to do this 100,000 times. And I'm going to keep how many are marked, right? So I'm going to loop through this vector. I'm calling pickfish with n fish sub I. So I'm going to call 233 and I'm going to save that. So if I said there were 233 fish on that one call, one fish was marked on the second one. When I guessed 94, I got 5, right? When I guessed 234, I got 1, right? Et cetera, et cetera. So this n marked is the same length as this n fish, right? So the n marked tells me how many were caught on that second one. So all I did is generate fake data to look like what I did when I went out on my boat. So if, what I'm going to do here is say, well, I want to keep the n fish, which is my guess of how many are in the pond, where n marked is 5, right? Because that's what I really saw. So that's what I'm going to keep. So that's called my posterior distribution. And if I plot it, this is what it looks like, right? So this is my guess, right? These were my guesses for how many fish were in the pond that resulted in getting 5 randomly selected the second time. And so the median is pretty close to 100, right? So if I were to guess, I'd say there's about 100 fish in this pond. And we don't really have confidence intervals. We have confidence intervals, slight difference. And sometimes here I'm just doing a 50% confidence interval. So I would say there's somewhere between roughly 75 and 125 fish. I'm 50% sure that's the population of the pond. Okay. And that's how I'd make my inference. I'm making no assumptions in terms of normality here. This is clearly a skewed distribution, but it doesn't matter, right? This distribution represents the probability of how many fish I think are in the pond. And I usually just take the center. In this case, I took the median because it is skewed instead of the mean. Okay. So here's where things get interesting, right? So a Bayesian would say one of the advantages of this approach is you can define your prior to be anything you want, okay? And that is advantageous because, a Bayesian would say to a frequentist, why you might have a lot of research that suggests this intervention is effective. Why are you evaluating this current iteration of the treatment against the null, right? You suspect the null is not true. Prior research tells us that, right? And so, um, right, so the Bayesians will leverage prior information to, you know, to define what that prior is going to be. So let's say, for example, I show up and there's a fisherman there. He says, I'm an expert fisherman. There's 200 fish in this pond. Okay. All right, great. So instead of using a uniform distribution, I'm using a binomial distribution centered on 200. So you could see I'm going to guess around 200 more, but I'm going to go all the way down to 20 and actually all the way up to 800 since I use the binomial distribution. Everything else here is going to be the same, right? I'm going to initialize an end mark. The only difference is I'm going to guess these values around 200 more. So if I repeat this over and over and over again, right, I'm going to keep the ones where I see what I see. And here's my posterior distribution. Now, I like to show this example because 200 is clearly a bad, right? This is an unreliable fisherman. He's really not an expert, right? So even when I defined a pretty terrible prior, my posterior still is around 100, right? The median bumped up a little bit, right? So the frequentist would critique this, right, and say, well, you could pick a prior that makes you say that something is more effective than it really is. But in my view, or in my experience, I think that criticism is overstated, and a lot of these things are pretty resilient to pretty bad priors. And if you go through a peer review process, people are going to call out bad priors. You have to justify your prior. And if you get into predictive modeling and you start using sort of Bayesian, there are Bayesian ways of estimating like logistic regression or regression, right? So the inputs and outputs look the same. Just how those parameters are estimated is going to be obviously different, right? It's going to generate the fake data, figure out where it is. And a lot of those are just going to use naive distributions anyways. And so, but I say all this because it turns out these kinds of methods work extremely well. The last thing I kind of want to talk about in terms of Bayesian analysis, I like to show this little app because really the first paper Bayes wrote had this kind of little silly game, and I thought it was fun, and so I built a Shiny app to do it, and it's just another example of showing it. And so he said, imagine this game. Imagine I have a pool table, and let's just say for argument's sake, the pool table has length 1. What I'm going to do is throw the 8 ball onto the pool table. You don't know where it is. What I'm then gonna do is throw balls, and all I'm gonna tell you is did this ball land to the left of the 8 ball or to the right of the 8 ball? And your goal is to tell me where the 8 ball is on the pool table. All right, so let's simulate this. So here's a little app. It's truly random. You could play with this later. So what I'm gonna do here, right? So down here, I'm gonna keep track of my priors and posterior distributions, right? So again, this is my guess, my initial guess. And so I'm starting with the uniform, meaning the 8 ball could be literally anywhere on the table. I know nothing so far. But now, Bayes throws it and tells me the ball landed to the right of the 8 ball. So let's just say intuitively, right? If you could imagine a pool table and the 8 ball somewhere on there and the ball landed to the right, intuitively, that means the 8 ball is probably more likely towards the left side of the table. And in fact, that's what I do here, right? From this prior, my generative function is going to say, I'm going to, whatever number I'm guessing from this, I'm just going to draw a random number between 0 and 1. And if the number I generated is greater than that number, I'm going to throw it away. Or no, I'm going to keep it. I'm sorry, right? And then otherwise, right? So the posterior shows I think the 8 ball is closer to the left side. This is one iteration, right? And over here, I'm just going to keep track through each iteration. So here's would be the median. This is my guess. And this is a 50. I could change it, confidence range, confidence interval. Okay, great. I throw another ball. This ball also lands to the right. So now what I'm going to do is I actually now have prior information. So I'm going to take the posterior from iteration 1. That's going to become my prior in iteration 2. So these distributions are the same. And I'm going to run through that same process and, right, keep all the cases where it lands to the right. So now I think the eight ball's a little bit more to the left. And so I can do this a bunch of times. Third iteration also to the right. Now I went to the left, right? So let's see here. So this posterior became this prior. I ran it through. I got this prior. Now in iteration four, right? This posterior became this prior, but now it went to the other way. So now you could see the distribution kind of shifted. So it's like, oh, maybe it's a little bit more to the right. So I'll just do this a few more times, maybe 10 times, right? You could see I got one left, a whole bunch of rights, right? And you can kind of see it kind of honing in. And so when, at some point you could say, here I can actually show, right? So here's where the eight ball was landed at position 0.18, right? And that was at fourth iteration, this red one, and the rest landed to the right. So you could see, pretty quickly I captured it, right? So that's another kind of key advantage of Bayesian methods is that it works generally well with small sample sizes, right? So we can kind of capture things generally pretty well. And you could start this over and kind of run it. You can see where it is at the beginning if you wish. So right, so on this example, I'm trying to show how a, the posterior from one iteration can lead to the next. All right, so that's my crash course in Bayesian analysis. Are there questions? Okay, then I want to just do a couple of things on as an introduction to predictive modeling. So we're going to go back to our data set where we're trying to look at whether or not a student passes based upon how many hours they study. And so, the prediction we could, is gets the log odds, and we can go through and we can actually convert that to a probability. It's substituting in the same way we do with regression. We can kind of go through this on all the different ways. Now, the way I kind of presented regression, or actually everything in this semester, is really doing statistics for inference. And what I mean by that is we really care about how each of our independent variables are related to our dependent variables. And we pay very close attention to, model assumptions, and we want to look at that relationship, and we might even care about multicollinearity and those kinds of issues. Now, as data scientists, a lot of times you're going to be modeling for prediction. So you might care a little bit less about sort of some of the model assumptions. Really, what you care about is, can I make new predictions that are accurate? And I might treat my model more or less as a black box. Okay. I'm not going to I have a whole lot of things I could say about whether that's ethical or not, particularly in the state of AI. And I think there are certain situations where we should treat things as a black box. But in some cases, with like networks, they are indeed black boxes we often don't understand. And so, in order to do that, some things we're going to care about is, kind of overfitting. Again, is going to come to an issue and the like. And so our strategy to determine how good a model is going to be a little bit different. So I'm going to switch to a different example here. So here we're looking at, I want to predict heart attacks, right? This is probably a common problem in the sort of medical world, these kinds of things where we want to predict certain diseases or what have you. And so, um, and so we have a whole bunch of things like age, sex, cholesterol, et cetera, et cetera. And so I want to predict a heart attack. And so I could, well, first of all, there's some missing data here, and I didn't really talk about this, unfortunately, but in general, my recommendation for missing data is to use the mice package, which does multiple imputation. So it's pretty simple to do. For simplicity, I only did one missing data set. At some point, I will actually, while you guys are probably still in the program, I'm actually giving a talk in August at the Joint Statistical Meeting on a package that I created to do modeling with missing data instead of just imputing. That seems to perform better. So I will give a talk to the school at some time in the future, and I'll talk about some of the missing data things. So keep an eye out for that, probably in the fall semester. Okay. Anyways, this slide, a lot here, but you could probably copy and paste this and use this if you have missing data. So when we do modeling for prediction, one of the strategies we're going to do is kind of split our data set into a training set and a validation or test set. Okay. And in this case, I did 70-30. That's often where I start. If I have really big data sets, maybe I'll do 75-25 or 80-20. But I think I had 94, 294 observations. So I did a 70/30. The other thing we need to be careful here and pay attention to is what is our base rate, right? And so in this case, if I look at the proportional table of heart attack, so in my data set, 36.5% of people have a heart attack, right? So my what I mean by base rate is the simplest predictive model I could define is I'm going to predict no one has a heart attack. And if I do that, I'm going to be correct 63.4% of the time. Okay. So I need to do better than 63.4. And I'll come back to this in a moment. All right. Oh, and then you could see here, right? So I just did a random sample of the number of rows in my heart data frame, and I created two other data frames, one called train, one called test. So at this point, if I want to use logistic regression, right, I'm going to use the GLM function. I'm predicting the heart attack from all variables from the training, right? So what's key here is I'm passing in the training data frame and making sure I specify logistic regression. I might look at this. This might be interesting, but like I said, right, so I could see males are more likely to have a heart attack than females, et cetera, et cetera. But really all I care about is, can I predict who's going to have a heart attack? Next step is I'm going to look at the distribution of the fitted values. This is going to give me some sense of, at least initially, how good my model is. So, and I have two lines. The red line is the people who did not have a heart attack, and the green line are the ones that do. So if I think of the prediction as the likelihood of having a probability, right, I would hope that the ones that did, that their fitted values or their fitted, log odds from the logistic regression are more to the right than the other one. So right off the bat, this looks pretty decent. Okay. So now, right, and so the fitted values from that are going to be between 0 and 1. Right. So I'm saving a new variable in my data frame called prediction. But you know, the doctors are like, the log odds. That's just tell me, do you think this person's going to have a heart attack or not? So in this case, I'm just going to split at 0.5. So the value is greater than 0.5. I'm going to classify it as, yeah, I think this person's going to have a heart attack. Less than 0.5, no. And so what now I have is, this is called a confusion matrix. So what I have here on the rows represent my prediction, and the columns represent what I actually see. Okay. So in 58.5% of the observations, I predicted no heart attack and they didn't have a heart attack. In 9.7% of people, I predicted no heart attack, but they did. So that's a type 1 error. In 4.8%, I predicted a heart attack, but they didn't. So that was a false positive. And then in 26.8%, I predicted a heart attack and they actually had a heart attack. So my overall model accuracy is going to be this 26.8 plus 58.3, which is 85.3, right? And so our base success rate was 63, which means my model is almost 22% above guessing. So I will say that's pretty high. I picked this data set because it works actually kind of well, right? So that's a really good improvement. Okay. But the problem here is I'm making this assessment on the same data I used to train the model. So really what I need to do to avoid overfitting is test against the validation set. So first thing I'm going to do is, in the validation set, look at my base rate. So my base rate is 65%. So it's pretty close, right? Pretty close to what it was in the training set. So here now I'm doing predictions, and I don't think I showed this before. So on the predict function, I still pass it my regression output, but I give it new data. And so this is the test data set. And again, I have to split it at 0.5. And so here's my confusion matrix. So on this one, when I save the column, right, my accuracy is 84.27 or 19.1% better. And this is pretty common, right? So you can actually see that there is some overfitting, right? So I'm 85 and this one's 80. So there's about a percent difference. So not terrible, but in some instances you're going to do that. And so when you get into like 624, you're going to learn a lot more strategies on how you do this. But in principle, right, our goal is to, get this as high as possible on our test data set, right? And we're using that test data set since it's different than it wasn't using the training. It means we're not, it's the likelihood of overfitting is diminished. common other way we kind of look at this is called a receiver operator characteristic. So one thing I did here is just split at zero point 0.5, right? Because I needed to go somewhere. But sometimes zero point 0.5 is not the best split. So in a receiver operator characteristic curve, right, we're going to so we have these true positives, true negatives, right? So this is the same type 1, type 2 error rate, that tables that we looked at before. So in a ROC curve, we're plotting the false positive rate against the true positive rate. And we're looking at the accuracy as we change our threshold. So it's easier to kind of just go to it. So in this case, what I'm going to do is say, well, uh, if I cut instead at 0.05, I'm going to say I'm going to cut at 0.01 and then 0.02, 0.03. And I'm going to do that in increments usually of 1%. And I'm just going to plot that curve. So if I had perfect accuracy, right? So if all people who had a heart attack was, the predicted probability is 1, and all people who didn't was probably the predicted probability was 0, then this line would go straight up and straight over, right? And so sometimes one of the fit metrics we have is the area under the ROC curve, and that gives us a sense of that separation. So the closer to 1, the better. If my line is on the unit line here, this blue line, then that means my model's no more than guessing, right? So generally 0 0.5 is as small, would mean a model that's no different than guessing. Okay, so we can kind of see where that is. And what we're looking for in terms of the optimal cut point is where the distance of that curve is perpendicular to this unit line. The other way we could look at it is over on this right side. As I'm going across, as that threshold goes from 0 to 1, I'm calculating the overall model accuracy. And so in this case, if I split at 0.515, which is pretty close to 0.5, right? That would give me the best accuracy. We could see anywhere in this is, it's little variations. It's not going to matter so much. Sometimes you can get different ones. And when you have highly imbalanced data, meaning I can't remember what it was, 35, 65 in this case, that's not too bad. That's getting on the borderline. Like 70-30 is like really, and certainly 80-20, where you might have really imbalanced data. Then the threshold to have the maximum accuracy is unlikely to be near 0.5, right? So this is here. This function is in the visual stats package, so you have access. It's also on the other one. You could also look at it in terms of a cost curve. This you might want to do is if you want to weight type 1 versus type 2 errors differently in the same way we talked about null hypothesis. Okay. So the last thing I really want to talk about here is the caution on interpreting accuracy. And I sort of already alluded to this, but I think one of the most, there's a lot, but one of the classic, I think, examples where people overdid it was some researchers from Facebook in 2016. And this made a lot of news at the time, and people freaked out and said, we can predict people's sexual orientation with 90% accuracy using SVM is support vector machines, logistic regression, or random forest, right? And people freaked out. It's like, holy cow, that's just based upon what I like on Facebook, you can do that. But I went around at that time, and I think I read this 2018, and so I said, let me see, let me check Gallup. I remember just noticing a Gallup poll, and it said that at least at that time, 4.5% of people identified as LGBTQ plus, which means 95.5% identified as heterosexual and didn't identify that group. So I'm like, great, here's my model, as I'm just going to predict everybody's heterosexual. My model accuracy is 5.5% better than Facebook's, right? And so there's two major takeaways from here. Is one, don't overstate your model, please. And second, if you're trying to predict extremely rare events, these kind of accuracies is probably not the way to go. And it's just going to be a hard problem, and you're going to learn strategies in this program on how to deal with it. It's something I struggle with in a number of areas where I've had that. And I first and this is I'm not going to go into all the details, but really the first place I encountered was actually in my dissertation, because I used logistic regression to predict whether or not a student would choose a charter school versus a traditional public school. And there's a case where I had really imbalanced data. 3% of Americans attend a charter school, and 97% attend traditional public school. I'm excluding privates. Okay, so there's some percentage, but at least between traditional and charter schools, if you take that group, 97% would be public and 3% would be a charter school. And so I in that context where I'm using a quasi experimental design, I'm using a logistic regression to predict charter school attendance, and I interpret that predicted probability as what we call a propensity score, right? But it's just the fitted value. That's why it's this propensity score down here at the bottom. But I say, okay, well, this person's propensity score is zero point 0.2, which means they have a 20% chance of being attending a charter school, right? So my treatment versus control. But as I was doing some analysis and particularly visualizing it, right, I saw a situation where the maximum propensity score or the maximum fitted value was never like greater than 0.5. And so I had to deal with this in the discussion of my dissertation. I had to explain it. And this is an artifact of logistic regression. So let me explain what's going on here. So in this bottom panel, what I did is, okay, so I say entry. So I'm going to fit a logistic regression so with 200 individuals. And basically what I'm doing is saying, well, let me fit a logistic regression. Here's the distribution of the fitted values. And what I'm really interested in is the minimum value of the range of the fitted values and the maximum. So I think I do this 20 times each one. So each of these black dots has to do with a different random sample. And then this black bar is sort of the median of the max, and the bottom represents the median of the minimum. Okay, and this was fitted. So I simulated one large data set. I randomly sampled such that I had the same number of ones and zeros, true and falses in my logistic regression. And then as you move up, right? So the second one here, I simulated it such that I had twice as many zeros as ones, right? I had a 2-to-1 ratio, right? And then a 1-to-3, 1-to-4, all the way up to 1-to-10, right? Which is probably closer to what I have. And so what this just demonstrating is that as you're going to predict rare events, or as that ratio of the zeros and ones, true to falses, increases, the range of the fitted values, all else being equal, is going to shrink. Okay. So again, going back to like if you need to make a cut somewhere, right? Looking at these things would be really important. So in my case, I need to make my split somewhere else. Of course, I'm using the fitted values in sort of a different kind of context. So just some like trying to share some experience that or gotchas that you're going to encounter as data scientists going forward. Um, Sort of, I think, looking at the time and where we are. When I post this slide deck, if you're interested, I have some slides here on classification regression trees if you want to scan through it later on your own. And if you have questions, you can bring them up next week or in Slack or email or if you like. But that's kind of, I think, what I want to cover at this point. And this kind of covers, I mean, this is really the only pure statistics course you're going to take in this program. And so hopefully I gave you guys a pretty good foundation, because when you get into some of the, there are a whole variety of courses, but when you get into the predictive modeling courses in particular, like I'm thinking like 624, you're going to start doing a lot of modeling. And I think in that course, you're often not going to spend much time looking at the details of how these models are estimated. And I think a good idea to have a little bit of insight as to what's going on there, particularly when things go wrong. So you have some place to kind of figure out. That's usually when I care about, like, how is this really working, right? That's, I think, for example, like the maximum likelihood estimation, that shiny app and the interactive stuff, and where I drew the distributions, kind of grew out. It was in part a student question with a data set where it wasn't really working very well. So, and then I dug into it. So, uh, thank you guys for the thank yous in the chat. But I'll entertain questions right now. Otherwise, we can call it a night. Yeah, go ahead, Farhad.
Hi, Professor. Yeah, I got a question. Like, you touched at the topic about imbalanced
Mm-hmm.
outcomes, and I'm facing one in my project. It's like 88 to 12, and I was trying to do different approaches, like downsizing or upsizing, weighted. Which one is the best? Like,
Oh,
what do you think?
huh. Um, so that's a great question. Um, I, I usually don't upsample because when you
Yeah, that's
upsample,
what I was thinking too. Yeah.
you're going to increase your n,
Mm-hmm.
and if you remember, like all the standard error estimates have n in the denominator, so you're likely to shrink your standard errors and reject null hypotheses, particularly in terms of coefficients, when maybe you shouldn't. So I generally downsample is the best, in my view, the best approach. Um, I don't have this in a general way, but I wrote a package called PSA boot, which is really meant around propensity score analysis. But there's a strategy I used in there where I have imbalanced data where um, you so if you have like 10% to 90%, let's say,
Yeah.
I could do like bootstrap samples where I mean, I'll always use my 10%. Like, so I'm going to say just because I'm going to think in this a propensity score analysis, right? So treatment people, I have 10% of my sample is treated, 90% are in the control. And I want to make a model that predicts whether or not people are going to do this treatment. Okay. So what I might do is say, I'm going to take 100 random samples of the of say I have 100 and 1,000, right? So I'll take a whole bunch of random samples of 100 from my control group and just keep all of the treatment ones every time. Okay. And then,
Mm-hmm.
right. So, and then pool the variances across all of those, so it's kind of a pseudo bootstrap, if you will.
Yeah.
Except I'm actually not sampling with replacement. I'm going to sample without replacement because I'm only taking whatever 10% to make it match the other one. So that's a strategy I've used. And then I'll plot the distributions. Uh, and that works out nice in terms of like, I do that and then I may report only one of those, but it lets me know if there's noise in the data that I need to be concerned about. So that's a
Mm-hmm.
strategy I've used pretty well in the past. Does that make sense?
Yeah. Yes. So you said like downsampling is a bootstrap.
It's like a not really a bootstrap, but it's like I'm gonna down because one of the criticisms I actually heard this at a conference this past week where someone um they used a weighting strategy because it's like we didn't want to throw away data. And I get that, right?
Mm-hmm.
So,
Yeah.
but again, when you have that imbalance, some of these, particularly the parametric methods like we learned in this class, are going to have some problems. So my choice was okay, instead of throwing away the data, I'm just going to estimate a bunch of models where I always have the the smaller class and just random samples so they match and just do it over and over and over again. And if all the models are kind of behaving relatively the same, then you're good. So I wouldn't call it a bootstrap per se, because a bootstrap it presumes sampling with replacement. So I'm sampling without replacement a whole bunch of time. The other way to think about it, like, is if I had the other way you could do it is say I have 100, say I have 100 zeros and then 1,000, right? Uh, so I can create 10 data sets and I just randomly assign every observation in that, so that control group, a number between 1 and 10. So I'll take all the ones compared to my treatment group,
Oh,
all the
yeah, yeah.
zeros, right?
Now I
So
got
I'm
you.
going to train
Yeah.
10 models,
Yeah, yeah.
right? All right. Does that make sense now?
Yeah, it makes sense now. Yeah,
Yeah.
yeah. Thank you.
Then
And
I'm using all the data, but I'm not using it at the same time.
yeah, I didn't know about much about logistic regression, but like I tried to experiment like with backward selection, like
Hmm.
in linear regression.
Yeah.
I don't know if it's approachable or not,
Well, the
like
other thing I would
p-values.
do is look at these slides. So you're going to learn in detail classification regression trees. I think in 624, maybe even 622 if you take that. Um, uh, uh, um, you know, that's a non-parametric method, so it doesn't assume anything. Like so, right. So we're doing this recursive partitioning. So like, I said I wasn't going to talk about it, but here I am. So let's say here's our space. We have two predictor variables, X and Z, and we're trying to predict classes A and B. And
Hmm.
so what it's algorithmically going to go through, it's going to say, well, let me cut Z here in increments as you go from left to right. And then it's going to try to cut X left to right to see, oh, can I separate the A's and B's? So on the first pass, it says, oh, well, if I split at three, Z at three, that'll be my first kind of split. All right. And then it's going to take, I'm going to look at the left side and I'm going to split going from whatever 0 to 3 on the Z and on the X. It says, oh, well, now on this side, if I split it 6, right, now I have this cell that's only A. And then this cell that has a mix, it's going to try to iterate this again. And it says, I can't really split to separate that. And then it looks at the right side, right? So we're actually building a tree. So now if I get a value of like less than 3 and greater than 6, right, I'm going to predict it's an A. These are all B's. And then this, what you do is the predicted probability is going to be the ratio of the A's to B. And this is kind of how we would visualize it, right? We're going to say, well, if X is greater than Z, so in this case, if Z is greater than 3, then we go down one side of the tree and et cetera, right? So there's no distribution assumptions. It's just going to kind of determine this algorithmically by splitting. And this is only with two variables. So you can imagine when you have a lot of variables, this kind of gets kind of complicated. And this going into how it does all that stuff. So you can see here, here's another example where I'm going to predict house prices from just longitude and latitude, right? So I get this tree. So the darker the color, the more expensive the house. And so
Hmm.
this is Southern California, right? So here's LA and here's San Diego, right? And so just using longitude, latitude, we can actually model this pretty well. Of course, the closer to the coastline you are, the more expensive the house, the more inland you go, right? And then there's things you can do, and so this might be overfitting where I could split a little bit further. These values in the boxes are the log median house prices, right? So you could do this with classification. So here, the example I'm going through is predicting who survived the Titanic from just a couple of variables, right? And so again, if you're a female and you came down here and you had a first class ticket, and you had no siblings, you were likely to die. But if you didn't have siblings and you were young, you were, so you could
Yeah,
kind
yeah,
of, right. And then there's a whole thing on ensemble methods. But anyways, so I would use that because that classification regression trees tend to handle imbalanced data a little bit better than say logistic regression. So, and I'm often doing both. I'm almost always doing logistic regression and random forest together. Um, Mostly because logistic regression gives me nice output. It's interpretable. I can understand what variables are significant predictors. Random forest gets a little bit more complicated, but tends to perform better
yeah.
in
I don't
general.
know nothing about random forest yet.
So
I'll study it later in
yeah,
64 I
you're
think.
gonna yeah. I don't want to overwhelm everyone, but and you're gonna do it in another course. Random forest is just another tree method, but it just does a lot of trees. So it's a combination of like bootstrapping. You're doing bootstrap samples and randomly selecting variables as you grow a whole bunch of trees. So
Hmm.
typically when you do a random forest, you're gonna like estimate 1,000 trees, and then your prediction is gonna be sort of a weighted vote across all those trees based upon which trees predict better than others. So um anyways, a paper I really, really love. Do we? Oh, look at that! It comes right up immediately up on my search because I search for it all to share it all the time. But this paper here looked at 179 different classifiers. So this is only doing uh classifying, which means that would be like logistic regression. That's one of the ones they look like. So
Yeah.
179 different prediction models against 121 data sets. And sort of their conclusion was, random forest performs really well most of the time. If it's
Mm.
not the top performing model, it's like very close to the top performing model. So this is a nice paper to have in your back pocket. There is one newer one that I've been looking at. So I actually had worked with some students in independent study last year that we still trying to wrap up that paper, but we tried to update that with other data sets and other models. There is a XGBoost, which is another tree method that performs really well. That wasn't included in that paper because it didn't exist yet. So anyways, I digress there. There's a question. So, okay, so let's check this. Somebody's saying the example slide deck is not working on the course site. So let's see here. Let me make sure to open it. Oh, um, did you click or use the arrow button? Try that. Let me know if that works. You use the arrow buttons to kind of go left to right. Um, okay. Another question from William. Um, not related to the lecture. So that's fine. I don't mind that. So question, R versus Python. Um, you're gonna do so I don't have the program map in front of me. Let me see if I can. I think I have it pinned in another browser. I have too many windows open. So you're gonna do both for sure. Um, I can't remember what Anna recommends. So my pleasure. Oh, no, I'm not talking to you, Siri. I'm sorry. Oh, Advanced 602, I think, is Python. So I don't know if you're doing that one. So that'd be Python based. Um, okay, so you got it to work. Great. The slide deck. I think 622 and 624 are kind of a mix of both Python and R, if I recall. So, uh, yeah, I could say a lot more. I don't want to go into Python R. Obviously, I've been doing R for a long time. I'm doing Python for large language modeling stuff now. And you know, maybe it's just because I've been doing it a long time, but I really, really like R a lot. So, um, oh, yes. Will the class website remain? Yes, I was going to talk about this next week. So if you notice in the URL, it says spring 2025. I usually just type data606.net. And if you notice, it does a redirect. So the one thing I would recommend is at some point over the summer, the 606 without like the subdomain will eventually redirect to a fall 2025 website. But yes, this will stay here. And you can go a step further. And if you go to the GitHub repo, which I would not recommend doing for maybe another 2 weeks until it kind of stabilizes, you can always come in here and either clone the repo or you can go to the code and download a zip file. And this will give you all of the content. So all the slides are in the slides folder in PDF and HTML format. The website lives here. You could run it locally if you look at this build.r script. So it's kind of complicated, but I think because I automate a lot of things like so there I have a schedule Excel file, and so all of the YouTube posts and things kind of are built automatically. And then this I have a build in order to build the PDFs from the HTML slide. Oh, here it is. This bit right here. You can run the whole website local that way. I'm trying to think. All the course data is up here. Yeah, so you could just download. Yeah, here's all the course data. The doc. Actually, you know what you could do is if you download it, this docs folder. If you just double click the index.html, that's the website. And if you didn't attend, I showed a little bit on how to do this because I'm using GitHub Pages. But I did. Oh, wrong website. Uh, if I go here to talks, I'll put this link in. I don't know if you went to this. This is a link to the recording that I did earlier this semester on how to use GitHub and GitHub Pages to build a portfolio site, which I would highly recommend doing. Start early because don't do it when you're on the job market. Like try to keep it up to date is my recommendation. Presentations, 10 minutes. No more than 10 minutes, please. 10 minutes. Did I not put that on the thing? 10 minutes. Good question. Uh, yeah, and I have the checklist. Here's the rubric. Yeah, 10 minutes. And you only need to come to the time slot that you are signed up for. And I'm noticing they're getting full. So if you did not already sign up, and you cannot do the noon to 1:30 on Monday, there's two slots there. Email me ASAP so we can figure it out. If there's enough, I can add a session. Otherwise, we'll just tag you on to somewhere. But hopefully, everyone signed up now. I pestered people last week who I didn't see signed up, I think. Any other questions? All right, then we'll have a quick administrative touch base next week. That I like to tell you a little bit about some of my research so that you know what I do, and if you want to reach out in the future. And from time to time, I'll do independent studies or sort of special topic courses. Sometimes on based on your suggestions, if like you're interested in something, or a lot of times related to my DAX research, if there's some kind of project. I had a student who I worked with in the fall. Actually, I just heard we worked together and he got his paper accepted to the joint statistical meeting. So he's actually we're gonna go to Nashville together and present. So that's kind of cool. He was a 606 student a year or so ago. So, all right, have a great night, everyone.
Thank you.
Thank you.